Hi, my name's Elijah Hobbs, and in this lecture I'll be covering the dynamics of a hovering helicopter. First, we'll go over some of the basics of helicopters. So the primary thing we want to do with a helicopter is move it upwards, and that is accomplished through the lift force, which is generated by the main rotor, and that will point perpendicular to the main rotor. In this diagram, it's in the positive j-hat direction. That is opposing the force of gravity, which in our diagram is pointing in the negative j-hat direction. So we need that lift to equal or be greater than the force of gravity. In our case, we want to hover, so we want them to be equal. We'll get into that in more detail once we cover the actual dynamics. But in order to get that lift force, we need to spin the main rotors, and because of the motor spinning the main rotors and Newton's third law, we will incur torque about the main rotors that will also be perpendicular to the main rotors. And so we need to deal with that torque so that we don't have the helicopter spinning. And we accomplish that through the lift force from the tail rotor, which will oppose the torque generated by the main rotor and cause us to stop spinning in that direction. So that force will be perpendicular to the tail rotor, and through the radius away from the center of mass, that will stop the torque generated by the main rotor. However, that will also generate its own torque through the spin of the motors rotating the tail rotor, and we will deal with that through the torque from the main rotor blades that's caused by the movements of the swash plate, which we'll get into in a lot more detail now, but for now we don't really need to explain that. And so that will stop the torque from the tail rotor to cause us to rotate. So we can stop both of those. We also need to prevent the actual force from the tail rotor from moving the helicopter in space, and so that is accomplished through a lift vector from the main rotor that is not entirely vertical, and we'll get into how that's accomplished later. But for the final force, we have drag, which will oppose the motion of the helicopter, but in our scenario we're covering a hover, and so the helicopter will not be moving, so we can safely ignore drag since it's dependent on the velocity of the helicopter. Now we need a bit of an explanation of what a swash plate is in order for us to explain the torque from the swash plate and why it helps us out. So essentially what the swash plate is two plates next to each other, one lower swash plate which is non-rotating that has three push rods that can move it in any direction, and then an upper swash plate which rotates with the blades and is then connected to each helicopter blade and controls the angle of attack of that blade. So essentially how the system works is the bottom plate is pushed up and down, and that allows us to force a rotation on the helicopter blades whenever they spin to that area of the swash plate. So this essentially allows us to cause the angles of attack of the helicopter blades to change at a specific point in their rotation. Since we can do that, and lift is dependent on angle of attack, we can cause an increased lift in certain points of the rotation to cause a lift imbalance, which then allows us to generate a torque so that we can cancel out the torque from the tail rotor. So that's essentially what the swash plate is and why it allows us to generate a torque that is very helpful in canceling out the tail rotor. I mentioned earlier in this lecture that we needed a lift from the main rotors that was not entirely in the j-hat direction so that we could cancel out the lift the k-hat direction from the tail rotors, and how we shift the lift vector into that direction is through gyroscopic precession. So I mentioned in the last slide that the swash plate allows us to create a torque through imbalanced lift, and through gyroscopic precession we can use that torque to shift the moment of inertia of the helicopter to shift where our lift vector is. Since the moment of inertia and the lift vector will always be perpendicular to the spin of the rotor blades, they will move together. So essentially how gyroscopic precession works is that you have an initial moment of inertia, and then when you add the torque vector to that divided by time, you are able to get a new moment of inertia. And so if you look on the diagram, you can see the initial moment of inertia, the torque vector applied to it from the torque generated by the swash plate that allows us to get a new moment of inertia that will cause the blades to be in a more favorable direction to us so we can have a k-hat component lift. Essentially, how this will actually work in flight is the helicopter will generate more torque than is necessary to cancel out the torque from the tail rotor so that it can turn the blades, and then it will generate less torque once the blades are at a favorable position, and so then the torques in that direction can reach equilibrium, and then it can hover steadily in that state. I also wanted to cover how the main rotors of the helicopter are able to turn so that the lift vector has components in the j-hat and k-hat direction. So essentially, all the helicopters in this configuration will have what's known as a flapping hinge, which allows the helicopter blades to move during flight so that they can achieve that off-axis position. And so I just wanted to cover that that's how the helicopter blades are moving, and so the actual rotor that's being turned still remains firmly in the j-hat direction, but the blades themselves will hinge so that they can move into that off-axis rotation. Finally, we can group together all the topics we've covered so far to fully describe how a helicopter is able to hover with zero velocity. So first we'll take a look at the sum of forces equation, which must be equal to 0. And we can see that we can have the lift term from the main rotors multiplied by sine of theta, the angle that the main rotors is against the axis, minus the force of gravity can equal 0. And we can determine that based on the rotations per minute of the main rotor. So we can control that and modify that. And then we have the lift generated by the tail rotor must be equal to the lift of the main rotor multiplied by cosine theta. So we can again make sure both of those are 0, so that can balance out. And then finally we have the torques. And again, we can ensure that all of the torques equal to 0. So we see that the torque generated by the main rotor will be canceled out by the torque that is generated by the force of the tail rotor multiplied by the distance r that it is away from the center of mass. So that will equal 0, and that torque will be canceled out. And then we have the torque generated by the tail rotor that we also needed to account for. And we can see that that is accounted for by the torque generated by the swash plate. And so that torque will cancel out the torque from the tail rotor, and so everything will balance out to 0. And of course, a lot of this will depend on the actual aircraft specifications and the specific rotations per minute of each rotor, but we can control all of that, so we know that this equation can balance out to 0, and this shows exactly how a helicopter is able to hover while having 0 velocity. Finally, I have a slide that details some of the references I used to make sure all of my information was accurate. So I have a textbook, a few articles, and then a couple of YouTube videos which were very informative. And I'd just like to thank you for listening to my lecture.